Yeah, so this is the second lecture on relativity, and I'll be giving you a brief introduction first, followed by a history of the way in which we think about space-time through the ages. That gives you some perspective about where we are today. And second, a very important physical idea, which was used by Einstein to come up with the general theory of relativity. It's called the equivalence principle. This basically maps the whole problem of physics into geometry. Yeah? And then we have to understand what geometry is and curvature is, and that's basically what Einstein's theory is all about. So finally, I'll just say a few words briefly about the dynamics of the gravitational field and conclude with a few general remarks. Okay. So what I'm doing actually is similar to what I did yesterday, trying to make it both advanced and elementary at the same time, because there is a range here. Some people already know the subject, others are coming to it. So the advanced parts are arguments that you will not learn in a normal course in GR. The elementary parts are the things that you will, if you have not been exposed to it, you will find it to be enlightening, even if you know the tensorial approach to GR, which is what most of the courses deal with. They deal with the mathematics, but the physics and the basic common sense part of the subjects are left out when you take a very formal tensor calculus approach to GR. Okay, let's start with the introduction. There's been a lot of interplay between physics and astronomy right from the beginning. To start with, of course, the ancient Greeks, they had some ideas about the planets they used to look up, but they used only their eyes to look at the sky and try to plot things. Of course, they achieved quite a lot despite this. They measured the circumference of the Earth. There were great achievements at the time that they knew that the Earth was round, despite stories you hear to the contrary. But the interplay between physics and astronomy came when you look at optics. People were studying optics, grinding lenses in Holland mainly, and they made devices like microscopes, which let you look at very small things. They also made telescopes, which make you look at very faraway things. Now, both directions are interesting. As you go to the microscopic world, if you keep going, you'll end up with quantum mechanics. And if you go into the macroscopic world looking through a telescope at bigger and bigger things, you get into gravitational effects. And today, right now, there's tension between the extreme microscopic world of particle physics and the extreme relativistic world of cosmology. But I'm just using this to say that by using instruments that are designed based upon the physics of optics, of lenses and all that, we're able to see much better. And in fact, into the heavens. And Galileo turned the telescope. Well, first the telescope was used for military purposes, for detecting ships that were coming in to attack you. For example, Galileo was trying to sell the telescope to the Senate in Venice, telling them that a young man with good eyesight, probably also a young woman with good eyesight, can see a ship coming in 2 hours before you can see it if you use the telescope. But then he also turned the telescope upwards to the heavens. And there he noticed features of the moon that made it look like something you could understand. There were craters on the moon. There was all kinds of structures which were not so clear to him before. And for a long time, it was just optical astronomy, looking at the sky through light. During the Second World War, people started using radio waves to detect incoming planes. That again has to do with warfare. And after the war, many of the people who did radar work during the war turned their attention to radio astronomy. They realized that the sky was full of radio waves. A lot of it was coming from the galaxy. That's another story, which I won't go into. You'll hear it from the other talks. Now, when you look in the radio wavelengths, you can see far deeper into space than you can with optical, because optical light is blocked by dust in the galaxy. So here you can see clear through to the end of for quite some distance. And if you see deeper into space, you're looking also further into the past, because light takes a long time to get to you from where it started. For example, during the supernova that happened in 1987A, in 1987, it's called 97A, it came from a dwarf galaxy. It was emitted from there 30,000 years ago. And if you look at light that we receive today, some of it was emitted from galaxies which are 1 billion years away, and or millions of years away. At the time when light left the source, there were dinosaurs on this planet, right? So you're also looking back into the past and the early history of the universe when you use probes that go deep into space. With radio astronomy came the discovery of very energetic sources like active galactic nuclei, which are black holes sitting at the centers of galaxies, swallowing matter and creating a lot of energy. There's also supernovae, which are explosive events that was actually detected in 1054 by the Chinese and possibly also by Indians, though we don't have a record of it. And neutron stars, pulsars. And this is the birth of relativistic astrophysics. And this is where our ideas about relativity, space and time come in. You need to have a grounding in relativity if you want to do any of these topics. Yeah? Trying to do, astronomy today without a grounding in relativity is like trying to do accounting with the Roman numeral system. It's very difficult. You have to understand the information that you get from the universe, you must have a thorough grounding in relativity. So physics helps astronomy in one way. It helps by building instruments. All the radio telescopes are based on electronics and things which we understand from elementary physics, from fundamental physics. And as well as once you get the observations, you're trying to figure out what is going on up there. Even at that stage, physics help us. And believe me, every branch of physics is represented somewhere in astronomy, whether it's fluid mechanics, electromagnetic theory, you just name it, you'll find it somewhere or the other. And for physics, astronomy provides extreme situations for us, extremes of density and strong gravitational fields, which we are not able to get on the planet. On Earth, we don't find such strong effects. So we're able to test relativistic ideas using astronomy. The finiteness of c, of the speed of light, led us to challenge our very ideas of space and time. And I want to go through the history of our ideas of space and time. This was the introduction, that's over. Let's get into the history of space and time. If you go back to the ancient Greeks, they thought of space and time like this. Here was space, and here is time. And if you draw vertical lines here, those lines are at the same space point for all time. You can also draw horizontal lines here, which are at the same time for all space, right? This was Aristotle's picture of space. There's no mention of the speed of light here at all. There's just space and there is time, and there is this grid of here vertical lines, now horizontal lines. And Aristotle believed that a body which is kept at a particular position will remain there until you force it to move. If you force it to move, it will reluctantly move by this formula. By the way, Aristotle was not as precise as this. I'm just translating what he believed into modern language. So this means that the natural state of a body is a state of rest, and motion is considered to be the result of a force which moves it. Now, actually, this is not such a bad picture of space and time if you talk to a bacterium. A bacterium is in a dense fluid, and it's a very viscous fluid. Like water is a very viscous fluid for a bacterium. And unless you apply a force, nothing will move. You put an object into the dense fluid, it will stay exactly where it is. If you apply a force, it will move. As long as you apply the force, then it will stop almost instantly. So this is actually a very viscous world. The world of Aristotle has equations of motion which are first order in time, like this. Now we come to Galileo. Galileo got rid of the idea of a here, but he kept the notion of a now. So there's no point in saying all these points are at the same point in space. There's no such idea. And the state of motion, which is natural, is uniform motion. So if you apply a force, it will change the velocity, but if you don't apply a force, the velocity will stay constant. Yeah? This is a different idea of space and time. But you can see now that what has changed from Aristotle to Galileo is the symmetry group of space-time. So let me go back now. This has got certain symmetries. I can translate in time, that's one. I can translate in space, that is three dimensions of space, so that's four altogether. Apart from that, I can rotate in space. So a total of 7 symmetries. That's the Aristotelian group, 7 dimensions. When you come here, you find there are 3 more, and those 3 more corresponding to moving with a uniform velocity in some direction. So that makes it 10, and that's the Galilei group. When you got to Einstein now, you lose the notion of now. But what do you get? You get the notion that light rays are the same for everybody. So what is preserved here in Lorentz transformations is these lines. What happens in the Lorentz transformation, this gets stretched and this gets compressed, or the other way around, but the lines are the same. Yeah? So here, there is again 10 dimensions. I mean, there's a 10 parameter group of symmetries, and they are different. The transformation laws of composition are different, but the number is the same. So in that sense, the principle of relativity did not start with Einstein, it started with Galileo. All these spacetimes are homogeneous and isotropic. Aristotle, Galileo, and Minkowski, which you just saw. I just said all this. Einstein just modified the principle of relativity, didn't give it up or didn't discover it. And there's a difference here between straight lines and curved lines. So straight lines are the natural state of motion of particles which are not acted on by forces. Curved lines happen when there is a force acting. So acceleration, we only consider inertial observers, those observers who are moving in straight lines. Now, the main idea behind general relativity is that space-time is curved. Yeah? But there's a small asterisk here. It tells you small pieces of it are flat. So that's what the whole lecture is about. What do we mean by saying space-time is curved? And what do we mean by saying that small pieces of it are flat? So let me pause here for questions, in case there are any. Yeah. Okay. How are they 10? Okay. I'll write down all the 10 and then I think I should switch on this light, no? Must be a... That's one. Space translation is 3. Space rotation is 3. This is total 7. So this is Aristotle. So all these are true also for Minkowski and Galileo. So for Minkowski, you have time translation, space rotation, and in addition, you have space-time rotation, which is what a Lorentz transformation is. And what I mean by this is not with cosine and sine, but cosine and sine, the hyperbolic rotation. So that's the extra 3 boosts that you get from Minkowski. And if you take the non-relativistic limit, you get the boosts of Galileo. So those are the 10. This is 7 plus 3, 10. I hope that's clear. Yeah. Okay, today there's nobody online, right? Okay, then go on.
So they said Galileo had 10 dimensions.
Yeah, Galileo also had 10, yes.
These are the same thing as in with the Minkowski, right?
No, these 7 are the same. Yeah? Yeah, but in addition, the form of the boost is slightly different. The boost means going to another frame. In Galilei, it is x going to x minus vt. That is uniform motion in the Galilean sense. Galilean motion, uniform motion in the Minkowski sense is a space-time rotation. It's very much like a spatial rotation. Instead of rotating in the xy plane, you rotate in the xt plane. And you don't use cosine and sine, you use cosine and sine. So mathematically, it's... I'm sorry. Oh, sorry. So how do we do this? Okay, is that right? I think this is enough, right? That's still visible, so I don't have to turn that on. Okay, so this is basically the thrust of the rest of this lecture. So general relativity is telling you that space-time is curved, and we're going to understand what that means. But also that small pieces of it are flat, and we're not really going to have to worry too much about the curvature until we have to. So I'm going to prove to you that space-time is curved by a simple thought experiment. So this thought experiment involves buckets. These are all buckets. Right? These buckets contain atoms. All the atoms on the right side here are in their ground state. All the atoms on the left side here are in an excited state. Yeah? So they're the same atoms on both sides. The excited atoms have more energy, and therefore the left side has got more mass. Now what I would expect is that these guys will start coming down because it's heavier on one side than the other. For the same reason that the weighing balance comes down on the heavier side. So as they come down, if I don't do anything, it'll just come so that the heavier stuff is at the bottom and the lighter stuff is at the top. But I'm not going to stop at that. As everything crosses the bottom, all these atoms are in an excited state, right? When they come in here. What I'm going to do is to use a laser beam to do stimulated emission. You learned about this from Shiv. Yeah? Stimulated emission will, I send in one photon, I'll get two photons. I'll send one photon up here to excite an atom up there. And the other photon, I'll just keep it and cycle it around. So I put in two photons and I managed to get one photon to go and excite an atom over there. So I'll maintain the idea that the left side is always heavier than the right side. This will go on forever and we can make an infinite amount of energy. That's clearly a paradox because I'm able to extract energy from nothing. So what's the resolution of that? And also, what is a paradox?
For stimulated emission, we need energy.
From energy, what's that?
For stimulated emission,
Yeah.
we are giving
Yeah, but I get back the photon. I put in one photon and stimulated emission gives me two photons. So I send one photon up to excite the guy upstairs and I keep the other photon to do the next round of stimulated emission. So I'm not losing that energy.
It can be resolved by saying that while the photon is going up,
Yes.
it loses energy.
Very good. That's exactly the right answer. As the photon is going up, it loses energy. Even if it had h nu energy here, when it goes up there, the frequency will change and you'll get h nu prime. Okay? Just as a stone thrown into the air loses energy as it goes up, a photon which is rising in a gravitational field also loses energy. And energy for a photon is h nu. So it ends up losing frequency. The frequency up here is not enough to excite the atoms there. And you cannot keep this machine going. Yeah? So this is what a paradox is. A paradox is a truth standing on its head to attract attention. That's what you learn from this experiment. Now, if you look at this picture, this is one, here I've plotted the height against the space, against the time. Okay? Space is vertical this time and time is horizontal. I consider two crests of the wavefront. I've got an atom which is here, another atom which is there. And it might be an atomic clock or something like that. But if you have two crests here, and then you consider a light ray that's sent up over there. These are light rays going up at 45 degrees. I'll find that there's a slight difference between the period up there and period here. Because a clock which is kept at a lower place, if I compare it to a clock which is the higher place, the upper person will think that this clock is running slow because of the redshift effect. Yeah? So that means now I've got a parallelogram in which these lines are parallel to each other. This side is 1, but that side is not quite 1. This can never happen in flat space time. So that means that space-time is curved in a gravitational field. This argument is also due to Bondi, like the first one about relativity. Right? So now we have to, I've given you a physical reason for saying we have to understand curvature. Now let's get down to it. We start thinking more abstractly about Minkowski space-time. It's a set of points characterized by these 4 numbers with a geometry determined by this expression. This is a new way of thinking about geometry because we have minus signs here where we had only plus signs before. This thing is called a Lorentzian geometry and it has null vectors, that is vectors whose size is 0 but the vector is not 0. That's the direction of light rays. Straight lines are geodesics And we saw yesterday there are also extremal curves here. They are the maximum length paths in the space-time. Now, given a curve, I can view a curve as consisting of many small pieces, each locally straight. Yeah? If I take an arbitrary curve like that, if I look at a small part of it, I will not see much curvature. A tiny enough part will appear to be straight. That's a simple common sense idea. The same thing is true for space-times also. Can view a curved space-time as consisting of many small pieces, each of which is locally flat. I'm going to develop this idea further. So in Minkowski space, for example, if you use Cartesian coordinates, you get x mu looking like this. Particles travel in straight lines which have a constant tangent, which can be time-like or null. And if you apply a force, you get a curved line. But a small piece of it can be thought of as flat. And this is just saying that just as time and space transform in a certain way, you also have the idea that momentum transforms in a very similar way. And that relation comes from, you can use quantum mechanics to motivate it, because time and energy are conjugate, and momentum and position are conjugate variables. Now, even in ordinary flat space, I could write the distance as dx squared plus dy squared plus dz squared, and consider this as representing my geometry. But I could equally well choose polar coordinates and write it as dr squared plus r squared times d theta squared plus sine squared theta times d phi squared. These are spherical polar coordinates. Yeah? In this case, the coordinates were doing a double role. They labeled the points, telling you which point is x equal to something, which is that point, and they also measured distances. In this case, that is not true. R, theta, and phi label the points, but they don't measure distances. In fact, R has the dimension of distance, but theta and phi don't have the right dimensions for distance. So here, what we are doing here is writing the distance in this form. You can write this as gij dxi dxj, where now x are generalized coordinates consisting of r, theta, and phi. And these can be dependent on, you can see that it depends on r and on theta. So in general, it can depend on all the coordinates. So for example, grr is equal to 1, gr theta is equal to 0, g theta theta is equal to r squared, etc. So these are now functions of position. So that happens even in flat space if you choose curved coordinates, curvilinear coordinates. Now, the relevance of this will come out in a few more minutes. The equivalence principle states is the main idea on which Einstein based the general theory of relativity. And he described it as the happiest thought that he had in his life. Yeah? It's an experimental fact that all bodies fall together in a gravitational field. You can see that quite easily. If I drop this piece of chalk and this ball, for example, I mean, I won't drop them because I think it will not fall together because this one is, well, it's bigger, it'll have more air resistance. But if I take two pieces of chalk, I think you will be able to see that contrary to what Aristotle believed, you'll hear only one click. They both fell at the same time. Yeah? And it doesn't matter the color of the chalk, the material from which it's made, all that stuff doesn't matter. People have done experiments to detect whether different bodies can fall differently in a gravitational field. They've never been able to find any difference. Yeah? So I'll talk a little bit about the experiments in a minute. One thing is to just drop things together and see if they fall together. The other idea is that there's a difference maybe, and they're all related ideas. Okay, there's the idea that mass has two different roles to play. Mass has an inertial role, the resistance to motion, That is, if it's in a certain state of motion, it will stay in that state. The other is that it responds to a gravitational field. And these two are different notions, but they happen to be the same in nature. So, to give you an example, suppose I take the planet Mercury. It's moving in the gravitational field of the sun, and it's subject to a force F, which is equal to G m gravitational upon r squared, where this is the mass of the sun and this is the distance from the sun to Mercury. And this G here says that that's the gravitational mass, the extent to which it's affected by a gravitational field. Now, if I write F equal to ma, what comes here is the inertial mass. In principle, it could have been different. In practice, it is not. The fact that these two are equal to each other means if I write mg, mi here times acceleration, means I can cancel these two quantities and equate the acceleration to just this quantity, gm upon r squared. Right? So that means that if these two quantities are the same for all bodies, acceleration will be independent of which body it is. Yeah? So that means that the motion of a planet, if I replace Mercury by Venus, it will travel exactly in the same way. So now the tests that have been conducted are of various kinds. One uses a pendulum. If I take a pendulum, you know that to derive the frequency of a pendulum, you have to write down, there's a, I don't know if you people are comfortable with these kinds of ideas, a Lagrangian. Yeah? So there is a half m theta dot squared plus or minus whatever, something g times 1 minus cos theta, right? And this has to do with mgh. So this kinetic term has to do with the inertia of the body. This has to do with the gravitational mass. So both the masses are appearing in this equation, in the Lagrangian for an oscillator. And when you work out the frequency of this, if these two are different from each other, the frequency will depend on whether you use one aluminum bulb or a gold bulb or a lead bulb. Right? Because on the other hand, if these two are the same, you can cancel this out. So people did experiments, and many of these experiments were done by, well, Newton, Bessel, all these people did experiments with pendulum to check if all of them had the same frequency regardless of the composition. You choose a length to be the same, and then you look for a change in the frequency. They found no difference. There's another idea called the torsion balance, which is, we start with the plumb line. The principle of equivalence also tells me if I make a plumb line made of lead and if I make a plumb line made of gold, they will hang in exactly the same way. Huh? Right? Why is that? See, because, what does it have to do with the principle of equivalence is that because of the Earth's rotation, there's an effective gravitational field which actually makes, if the two were different, it would make one go in a slightly different direction from the other. Because the inertial mass is what comes in the centrifugal force. It's a gravitational mass which comes in the gravitational force. Right? So two plumb lines would go in slightly different directions. Now what you do is you take a thin thread and you put a bar here and you have the two plumb lines here. If they're pointing in different directions, there'll be a torque on this thing and that will turn. So this is the torsion balance experiment. It's been done for a long time. Yurtwosh first, then large number of people, Breginski, and there are others whom I had not heard of until I looked it up for this talk. But there's been a lot of work here. And finally, the best one is some satellite experiment called the microscope experiment. It tells you that the equivalence principle is valid to 1 part in 10 to the 15. That's fantastic accuracy. So we're going to take it as infinitely valid. We believe that it's true. This means that in a freely falling frame, there is no gravity. Gravity can be eliminated by just falling with the gravitational field. Any observer who's falling in a gravitational field will see no effect of gravity. Now, there's a slight video I'm going to show you, which I made yesterday with the help from Hiya, Jyotismita and Mahek, and they took a slow motion version of this experiment, and I'm going to show it to you. And earlier on, I'd done it, but you couldn't really see it was going by too fast. And luckily, Mahek had a slow-mo app in a phone. I don't know what, anyway, you're going to see it now. So here's the experiment. That's a bottle of Listerine mouthwash in which I poked 2 holes. This is a very high-tech experiment. And so I filled it with water, and I'm holding it up there. And when I let it, first I'll hold it for a while. You'll see that the water keeps on falling from it. This towel is simply to catch it so it doesn't break and I can use the bottle again. Okay. And then when I leave it, the moment I leave it, you'll see that the water flow stops immediately. The water is flowing out now because of gravity, and the water is falling under gravity, but the bottle is not. But if they both fall at the same rate, the flow will stop. So that's what you'll see. Yeah? So this is now an experimental fact that all bodies fall together, and we can get rid of the gravitational field. So in a sense, there is nothing to understand. We can accommodate the gravitational field within special relativity by just eliminating it. Since all the bodies fall the same, we can think of the trajectories of falling bodies as a property of the space-time and encode gravity into the space-time. That's what we do here. This is the idea that Einstein mainly had, that you take, and this should be a tau, not s. This is a proper time. ds squared is g mu nu, x nu. And I think you all know this summation convention. Even if I don't write the summation, if an index is repeated, it's summed over. So Einstein's main suggestion is that gravity resides here. You tell me what these functions are, and that will tell me the nature of the space-time and how bodies will move in it. What you do if you want to find out how a body goes from A to B, draw a line between them, work out the total proper time, and extremize with respect to that curve, and you'll find the right way. And here, the xp are merely labels for the different points, and it's very similar to polar coordinates. Xp do not have the meaning of lengths. All the length information is contained in G. So you had coordinates doing 2 jobs before. One is labeling the points and measuring distances. Now you have 2 people. You've given jobs to the coordinates as simply as labels, and the metric, the distance information is contained in the metric. For example, I could take Minkowski space and write it in polar coordinates, and the coordinates there do not have the meaning or even the dimensions of distance, as I showed you earlier. Now, you must appreciate that we use numbers in 2 different ways. We use numbers as labels. For example, when you enrolled in a college, you get a serial number. That's your label. It'll be some complicated number, the year of joining, all that stuff. That is not, it's not significant quantitatively. That number is just a label. It's not measuring anything. Whereas if you measure the height or the weight of a person, that number measures something, the weight in grams or kilograms, or the height. Yeah? Those are, that's the other role for numbers. So they're called cardinal numbers and ordinal numbers. Cardinal numbers actually are telling you size in some sense of the term, and ordinal numbers are just telling you the number in a list. It's a label. For example, if I tell you, if I invite you for dinner, and I tell you that I live on Burley Street, and my house number is approximately 323. You'll be hunting around looking for your dinner. You can't find it. It's not useful. So if you want to find out if a number is cardinal or ordinal, just add the word approximately before it and see if it makes sense. So if I tell you that the Earth has a radius of approximately 6,000 kilometers, that makes sense. But not my phone number is approximately 9270. Right? Yeah. Question.
So when you think there is an object falling in
Yeah.
the gravitational field,
Yeah.
it experiences no gravity. And you think that it experiences no gravitational force.
Yeah. If you look at it from the point of view of the person falling with the.
Is there no force of gravity?
I don't care about the force. I just care about the acceleration. So this guy is accelerating at the same rate as the falling body. So he decides there's no acceleration.
Because we're not worried about the force. Because in a particle electric field will still feel electromagnetic.
That's correct. You're absolutely right. So let me tell you the main difference between electromagnetism and gravity. So in the language of forces, when a charged particle is moving in an electric field, the force is given by E times Q times the electric field. Let's not worry about signs and all that. The force on a charged particle is given by this. The acceleration on a charged particle is given by m times a. Yeah? So if I put these two equations together, I'll find that the acceleration of the charged particle is given by qe over m. Yeah? Now q and m, if this ratio was always a constant, then all bodies would fall the same. But there are neutral particles and there are charged particles, and they all fall differently. So what I'm saying about the gravitational field is not true for the electromagnetic field. And what I'm saying for the gravitational field is that acceleration will be given by the gravitational mass times the gravitational acceleration divided by the inertial mass. And if these two were different, then the principle of equivalence does not hold. But we have done experiments to show that these two are equal to each other, or the ratio is constant for all substances. So I can just absorb that constant in the definition of something. Yeah? Yeah, no, that's a very good question. It tells you that there is something special about gravitation that doesn't care about forces. So what I meant about not caring about forces is that if I go to that frame, I don't see any acceleration. And if I don't see any acceleration, I don't see any reason to assign a force there. Force is zero, I would say. Now, any point, okay. And at any point, an observer who's freely falling defines a local frame in which there is no gravity. This can be applied in every local patch to describe gravity. So does this mean that gravity is totally eliminated? And if it is, then we don't have to worry about it, we just eliminate it. But that's not true. It's only a uniform gravitational force that can be eliminated by falling. Non-uniform gravitational fields are real, and this is evidenced in the tides which you see. If you live near the ocean, there are tides which are raised by gravity. So let me explain this to you. Here is the Earth, and here are two falling bodies. And they are far apart from each other. So the direction of the acceleration is different between here and there. If I fall with these bodies, if I'm somewhere here falling in between, I'll see these two bodies approaching each other. So they're not falling freely. They're accelerating relative to each other. And similarly, if I have these two bodies, this is further away from the Earth and falling slower. This is closer to the Earth and falling faster. And if I stand in between them, I'll see this guy going away from me because I'm falling faster than him, but slower than that guy. So I will see a relative acceleration here and there. And this is what they call a tidal force. Tidal forces are real, and this is what is related to curvature. And now we are getting into curvature. Okay. So now let's forget about physics and just understand curvature by just talking about curves. Let's understand curvature in low dimensions, where it's much easier to visualize than in 4 dimensions. So it's clear that this line is not curved. This line is curved. This is closer to this than this one. This is less curved. This is more curved. So I get the idea that if I want to find out the curvature of a circle, I just define it as the inverse of the radius. How do I find the radius? Just take a tangent at this point, take a tangent at some other point, and draw the perpendiculars to the tangent. They will both pass through the center. And the distance from the center to the circle is the radius. And 1 upon that is the curvature. If you do that with the straight line, you find that these two lines are parallel to each other. They meet only at infinity. So the straight line can be thought of as a circle of infinite radius, and it's not curved. Now, given any curve, if you look at a small piece of it, you can look at the tangent and claim that a small piece of it is straight. So that is one approximation to that curve. A circle approximate to a second order, and its the curvature resides in the second order. To first order, all lines are straight. To second order, there's a curvature, which could be 0 or non-zero. Now let's go up one more in dimension. This was about 1 dimension. Consider a 2-dimensional space which can be considered as locally flat. For example, you can approximate it by its tangent plane. So let's take this, here it is. This is the surface of this thing, and I can approximate it. See, here's a flat something. Just touch it over here. I can approximate that bit of the ball by a flat plane. That might seem like a crude approximation, but just think, when you walk around, do you worry about the curvature of the Earth? You don't. So in this approximation, where you replace this curved surface by a flat surface, the Earth is flat. And it's a good approximation. If you're traveling around Bangalore, or even if you're traveling around, let's say within the suburbs of Bangalore, you don't have to worry about the curvature of the Earth. If you're building a house, you don't worry about the curvature of the Earth. So this is the tangent space approximation to the surface. But it does not capture the curvature. The tangent plane, by definition, is flat. It's a plane. The curvature appears in the next approximation, and the deviation of the surface from its tangent plane. That's what we'll talk about now. So in the approximation, in the tangent space approximation, the Earth is flat, and which is why it took us so many years. Many people still believe that the Earth is flat, but they don't realize that somebody in Sydney has a different flat space, and somebody in Bangalore has a different flat space. Yeah? And they can talk to their friends in Sydney, and they can find out from them that they're not living in the same space. But they don't do that. Okay. So what I can do is to take my XY, I take the ball and keep it on the table, let's say, and take the table as my XY plane and Z as the Z axis normal here. Then to a first approximation, I can write Z of XY like this. It's a Taylor expansion. There are no linear terms because the table is flat. Z does not rise with X or Y. I've chosen the tangent space to be the XY plane. And as a result, Z of XY can be expanded like this, where A, B, and C are coefficients. And by a rotation, in this case, it's not necessary, but let me take this thing, okay? There's a slight curvature like that and a slight curvature like that. I mean, there's more curvature in this direction than there is in this direction. So if I keep it over here, I can have different curvatures in different directions. And in fact, by rotating in the XY plane, I can get rid of the off-diagonal term. This is like diagonalizing a 2 by 2 symmetric matrix by means of rotations. Is that point clear? That you can get rid of the cross term? So you can reduce the surface to this form, kappa 1 x squared plus kappa 2 y squared. These, according to Gauss, are the principal curvatures. Actually, this was known to Euler also before Gauss. Kappa 1 and kappa 2 are called the principal curvatures. In other words, I can take the surface and keep it flat like that and keep taking cross sections. And I'll get curves there with different curvatures. The maximum and the minimum curvature are the two principal curvatures. Now, given two numbers, K1 and K2, you can do two things with them. You can take their average, which is the mean curvature, and you can take their product, which is called the Gaussian curvature or the intrinsic curvature. This is called the extrinsic curvature because it depends on the way in which that surface is placed in three-dimensional space. For example, if I were to flip the surface over, if I were to take a surface which is concave upwards and turn it down, both kappa 1 and kappa 2 will change sign. And that means that H will change sign because the sum will now change sign. But the product will not change sign. So the product is something which captures the intrinsic geometry of that surface. So a general surface can be written like this, and you can just, basically this is the way in which you work out the metric on the surface. You take Z as a function of xy, and you write dz in terms of x and y and square it. If you choose the tangent plane as the xy plane, you find that all the first derivatives vanish entirely. Okay. And this is very much like the equivalence principle. Because what you're doing when you're approximating a flat space by a tangent space is restricting attention to only the first derivatives. Similarly, in an arbitrary gravitational field, when you go to the local inertial frame, you're forgetting about the second derivatives of the metric and just looking at the first derivatives. And those can be made to vanish by appropriately falling. Now I'm going to show you some paper demos. Yeah, I'm not sure how much time this will take, but let me. So I'd like to. Yeah. No, just pass two to one. Two or three can share one. I'm sorry. Let me just hand these to people behind. So two or three share one, and I will save some time by just over here. Just pass it down. And actually, there are some more here which I didn't ask for, but they printed it out. So maybe you can all try it, but it'll be easier if you collaborate. Then, okay. Maybe I'll keep this for the next time. Oh yeah, and there's also some tape and scissors. So I want all these back to return it to these people. Yeah. So you'll find in these papers that there are three of them. So one has got 0 red lines. What's that? Oh, you didn't get a sheet. Yeah, these are not sorted, so you just you'll need to get 3 pages, one which has got 0 red lines, one which has got 1 red line, and one which has got 2 red lines. Okay? Now, what I want you to do is to take the piece of paper which has got 0 red lines on it. No cutting yet. Yeah. Take the piece of paper which has got 0 red lines. Which paper? Oh, scissors are. Where are the scissors? No, someone has the scissors there. Yeah. Now take the piece of paper which has got 0 red lines and just keep it on the desk like this. Okay. Take a piece of paper with 0 red lines and keep it on the table like this. Okay. Now put your thumb and finger in the middle and pick it up. It will flop over like that. Right? Yeah. Now imagine that this was a pizza and you picked up a pizza as you did this piece of paper. Then it would flop over and all the olives and the juicy, delicious stuff would fall off it. Right? Not good. Now do it differently. You keep your thumb in the middle and your fingers on either side and bend it upwards slightly and pick it up. You see, it doesn't flop over. Yeah? Now you can have all your toppings and eat them. Now, there's a bit of geometry contained in this idea. The intrinsic geometry of the paper is flat. So intrinsic geometry is defined by Gauss as the product of the two curvatures. If I have 0 curvature like this, I could have non-zero curvature like this in this direction without violating the intrinsic geometry. But if I have positive curvature here, which is what I'm doing, then non-zero curvature here means that this cannot be non-zero because then the intrinsic geometry would change. If it flops over downwards like that, negative curvature here times positive curvature here would mean that the paper has to be negatively curved, which is not true. It's 0, it has 0 curvature. I have a question? Okay. No, what I'm saying is that if you pick it up like this, there's 0 curvature here and non-zero curvature here. Oh, when I pick it up, I enforce positive curvature here.
But you're saying intrinsically it's flat.
That's right.
You're enforcing it to be flat.
No, it has to be flat because the paper has got that the distance relations between the paper don't change when I do this. If I am a bug living on the paper, it doesn't know that any distance inside the paper has changed. You need to?
To be flat, you need to put a positive curvature.
No, No. See, just let's distinguish between intrinsic and extrinsic curvature. Intrinsic curvature is zero for a paper. That depends on the distance relations between points. If I draw a triangle on the paper, the angles will add up to 180, no matter how I fold the paper. Now, what I'm saying is now I'm talking not just about the paper itself, but also the way it's sitting in the external space. Okay, now when I pick it up like this side is not being curved, but this side's being curved and it's flopped down. Okay, that's consistent with the Gauss's idea that the intrinsic curvature is zero. But if I now enforce a positive curvature here on in the extrinsic part, this part cannot afford to have a negative curvature, so it cannot flop down. So remember that when you eat a pizza. Okay, that's one. Okay, now you'll find a piece of paper which has got two red lines. What you do is carefully cut along the two red lines and take out 1/4 of the page. So if you do it neatly, it's better, but just a minute, yeah. And also you would have seen some arrows being drawn on the piece of paper. You'll follow the arrows, they're all parallel to each other. And you go around anti-clockwise, you find that they come back to themselves. Okay? Now what you do is you take the paper with two red lines and you cut all the way from one side to the center. Just see what I'm doing. Cut like that and like this. Okay? Now take out 1/4 of the paper and don't throw it away, keep it for you. Now what you do, you stick the two red lines where they were into a shape that looks like this. Okay, I'm not done it very well, but I think you people have better dexterity with your fingers. What you've made is a cone. This thing is a cone. When you stick these two things together, you have a cone. And now you notice you have a triangle here. You've got a triangle. The sum of the angles adds up to 90 plus 90 plus 90, which is 270 degrees. Yeah, that's curve geometry. The sum of the angles of a triangle don't have to be 180 degrees. Yeah? And then if you look at the arrows on it, in every small part, if you stretch it out like this, you'll notice that these two are parallel to each other, and these two are parallel to each other. But when you come across the juncture, you find that it's rotated by 90 degrees. And not only that, if you go anti-clockwise around this point, if I go anti-clockwise this way, I'll find that the vector is rotated anti-clockwise. So this one is said to be positively curved in the Gaussian sense. So here what I'm doing is taking a piece of paper which is flat. You use your flat intuition all the time. All the curvature is concentrated at a single point. This is a way of understanding curvature which is localized. I'm not sure I should okay.
No, about the arrows.
Oh, okay. Just follow the arrows. In each small part, you'll find that the arrows are parallel to each other. You can just keep the paper like this. You'll see that they're parallel. And locally, they're all parallel. But when you come back, you find that they've rotated by 90 degrees. And if you go around anti-clockwise, you find that the rotation of the arrow is also anti-clockwise. Yeah? So this is an idea about, this is what happens when you have curvature. Now, let's try to get this over with. I'm not sure if I should stick to the time. It's okay. I think we'll go a little over time because we have half an hour after this. It's more important that you understand this thing. Now, there was a piece that I asked you not to throw away. Yeah. Now, take the paper which has got just one red line. Okay, now cut along the piece of paper with it's got one red line, just cut along the red line till the center and insert the two red lines that you had before into, I'll show you how it's done. It's a little bit more complicated. First you lay it flat on the table. And you lay it flat on the table and stick the piece, the quarter piece on this one. And then you turn it like this and you'll find it goes off the plane and you stick the rest of it. Yeah? So you'll end up with something which looks like this. I took the quarter piece from there and stuck it in here. You can see already that this looks quite different from what we had before. Yeah? Okay, so what you do is, see, yeah, you cut that, then you keep this here like this and stick it. Oh, this, where's the red line? Both are red lines, yeah. Then here you stick a piece of tape like this, and then after that you do, okay, first you do that, you just stick a piece.
With this side as well?
Yeah, one sec, let me, okay, I'll do it for you. Sorry. Yeah? Okay. Now you just take this up like that and stick these two together.
Got it. Okay.
Yeah? So what you've now got is an anticone. That was a cone. This is an anticone. This has got negative curvature. And if you can think of this thing, if you look at it like this, you can imagine that there is a pass somewhere. Yeah. If you go to the Himalayas, you'll see that there are these passes that all the invasions into India and subcontinent took place through the Khyber and Bolan passes. So there are two tall mountains like this and there's valleys over there. So this looks like a saddle. This has got negative curvature. And now if you look at the arrows on this piece of paper and follow them around anti-clockwise, you'll find that if you follow them around anti-clockwise and come back, the arrows have now shifted in a clockwise direction. You might have to draw some more arrows. If you like, you just draw some more arrows. What you do is, for example, here, just give me your pen. Yeah. So this part is like that. So, yeah. Then I just draw it here. This is parallel to that. This is parallel to that. This is parallel to that. But this is not parallel to that. So when I go anti-clockwise like this has turned clockwise.
Clockwise, okay.
Yeah. So this is negative curvature. Was this yours or mine? Okay. Okay. Now you can also see other things about curve geometry. If you take a circle, you take a point here and draw a circle of some radius. In fact, let's imagine the top part is smoothed out so it looks like a shuttlecock. If you draw a circle, you'll find that the circumference is not quite 2 pi r. So there are many ways of characterizing curvature. The sum of the angles of a triangle or the size of the circumference of a triangle compared to the radius. Now, what I did now was to talk about curvature which is concentrated at one point. Next, I'll talk about curvature which is uniformly distributed. That happens for a ball like this. Here is an object which is curved, and it's curved everywhere. It's not just at one point. It's curved everywhere, but still a small piece of it is flat. Now, if I take 3 points on the Earth, North Pole, Ecuador, and Egypt, yeah, and I draw a triangle, I'll find that the sum of the angles is much more than 180 degrees. If I take a circle at the North Pole, the longitude, if you take the latitudes, I'll find that the ratio of the circumference to the diameter is less than 1. In the anticone, I'll find it to be greater than 1. All these ways are ways of characterizing curvature. And they turn out, okay, very importantly, I forgot something. Yeah. You take the flat piece of paper and you fold it over like this, you make a cone. Now the angle is 180 degrees. And you'll find that there are two straight lines. Here's one straight line, and there's another straight line. These two straight lines, huh? No, if you were to take, okay, let's pretend that this straight line is at the bottom of the page. Huh? And I just fold it like this. Now I've got these 2 points here, connected by one straight line over here and one straight line like that. So a triangle is a figure which is closed and has 3 angles. A biangle has got only 2 angles. So in a curved space, you can have a biangle. 2 straight lines can intersect each other twice. That never happens in flat space. So this is also related to gravitational lensing. If you think of gravitational lensing, you have a source putting out 2 beams of light, and they go like this, and they converge to each other in a gravitational field.
Positive curvature has a biangle.
In positive curvature, yeah. In negative curvature, geodesics deviate from each other. In positive curvature, they converge. Okay, now I think I should just move on. I'll quickly wind up because I don't want to get the organizers too mad at me. So this was about uniform positive curvature. This was about uniform positive curvature. My laser pointer is gone. And if I want uniform negative curvature, if I just take Minkowski space in 3 dimensions, take T, X, Y, forget about Z, because we're talking about 2-dimensional surfaces. Instead of putting the condition x squared plus y squared plus z squared equal to 1, I'll put the condition that t squared minus x squared minus y squared is 1. That will define for me a surface of constant negative curvature. It looks like a saddle, it goes off to infinity. And if I take this, the metric on the sphere which I wrote down, that d theta squared plus sine squared theta d phi squared, if I replace the sine theta by sine hyperbolic theta, what I get is a negative curvature. And I don't have time to talk about this. There's some way of representing the space by on the upper half plane by writing down this metric. And you find that the geodesics are actually circles which are normal to the real axis, to the x-axis. All these are geodesics, and you can see that there's a triangle here, and the sum of the angles don't add up to 180 degrees. It's less than 180 degrees for a hyperbolic triangle. Now, of all the different ways of thinking about curvature, one of them stands out, and that idea is the idea of parallel transport. You take a vector and you take it along a closed curve and bring it back, yeah? And you find that it's changed. This is the idea that Riemann had, and it's actually much better than Gauss's idea of multiplying the 2 curvatures. Because Gauss's idea is restricted to 2 dimensions, Riemann's idea works in any dimension and also in any signature. Even Lorentzian geometry, you can use Riemannian ideas of curvature. And you have what we call the Riemann tensor. That's a tensor that depends on it's a 4th rank tensor which depends on metric, first derivatives, and second derivatives. And that is what we use to describe the dynamics of gravity. In Newtonian gravity, the gravitational field of a certain density is given by this Laplace equation. Del squared phi is 4 pi g rho. In Einstein's theory, you have rho replaced by a stress energy tensor. It has matter in motion, it has got stresses also, and all that contributes to a tensor constructed from the Riemann tensor. And in the Newtonian limit, basically only g naught naught will survive, only the time component of the metric survives, and that is related to the Newtonian potential. There are some simple solutions of Einstein's equations. For example, this is the Schwarzschild solution, describing its analog of a point mass. It's static, spherically symmetric, and describes empty space-time except at the origin where there's a singularity. At r equal to 2m, there's no singularity, although it looks like it, but there's an event horizon, that's the black hole. And I'll skip over these things. I think you can probably get it from somewhere else. It shows features like the redshift, the bending of light, and there's also the precession of Mercury is all explained by this metric. And the bending of light is illustrated by the slide from the movie Interstellar. There's actually an accretion disk, but because we're looking at it from this side, the other side of the disk, the light from the other side is being bent over towards us, and it looks like it's coming from above and below the disk. So conclusion is that gravity deforms space-time. The theory of GR predicts black holes, gravitational waves, and they provide a new window to the universe, and this is going to be the wave of the future, the gravitational wave astronomy. And many of you were asking me what's a good thing to work on. This is an excellent area to work on. And also don't, go by your own intuition, find out what suits you better. I mean, what I tell you may be good for me, but not good for you. But this is definitely an area in which there are experiments and it's a growing field. And it's a good thing to work on that. I'd like to finally thank Karthik and Saurabh for the invitation to talk to you. I've enjoyed meeting you and discussing physics with you. And we can carry on the discussion outside. And thank you all for listening. Yeah.